Today we'll talk about a little bit different topic, which is also directly related to the trace map, but in a sense with different models that can be reduced to the trace map. Let me remind what the trace map is and how we obtained it. So as soon as you have this recurrence relation between matrices from SL to R, you immediately can deduce that for half traces of those that sequence of maps, you can obtain this recurrence relation. And when we did that and gave an explicit short proof of that fact, I emphasized that the fact that this recurrence relation on matrices implies this recurrence relation on traces doesn't depend on the explicit form of the matrices. Whatever SL to R matrices you have, one that implies the other. And we use that in the following way. For the Fibonacci Hamiltonian, we explicitly calculated that the first three traces had this form, and then you could understand the dynamics, the properties of other traces just using that relation. So we introduce the trace map, and we reduce the question to the following. You get that point, and you iterate that point under the action of trace map, and you want to understand the dynamics, the behavior of that orbit. In our problem, all the points that we considered were outside of the Cayley-cubic. They were on those surfaces where the dynamics is hyperbolic, and we use the hyperbolic dynamical system theory in order to understand the properties of the physical systems that are related to this trace map. So this is the Fricke-Vogt invariant, this is a family of surfaces, and we considered the surfaces that corresponds to the positive value of the parameter I. Question: what if the value of that parameter I is negative? Then you will get different surfaces, so we'll see them in a minute. But the question is, are there any actual models that can provide a necessity to consider the dynamics on those surfaces? The answer is yes, and there are many of them. One of them was suggested initially by Sutherland and then used by Romanelli to introduce the to relate the properties of so-called Fibonacci quantum walk with the dynamics. And there are, this is definitely not the complete list. So there are some problems that can be reduced to the question about the behavior of that sequence of matrices with that recurrence relation with the initial condition, which is inside of the Cayley-cubic, which lies on the surface which corresponds to the negative value of the parameter. So I don't want to discuss those models because this is just a motivation for us. And then here's what's happening. So this is a Cayley-cubic that corresponds to the zero value of the parameter. And then I want to change the parameter, but I will not increase the parameter as I did previously. So previously the parameter was equal to lambda square over 4. So it was necessarily non-negative for any coupling constant lambda. Now let me take that parameter to be negative. This is what happens. Those singularities disappear completely, and instead of appearing of the necks, we just have disconnected components. And the internal component, even if it doesn't look like a sphere, it is a sphere, smooth sphere. And when you change the parameter and send it to -1, it will be changing like this. So what we want to study now, we want to study the behavior of the trace map on that sphere. That sphere is invariant. And moreover, not only it's invariant, it also bears smooth invariant measure. It's easy to see because you have a smooth foliation. It's just foliation given by level surfaces of that Fricke-Vogt invariant. And on the other hand, trace map itself preserves three-dimensional volume. And therefore, that three-dimensional volume must split into invariant one-dimensional areas on the surfaces. So now we are totally in the context of the two-dimensional conservative dynamics, and that's exactly what we want to talk about today. The huge difference between the behavior in this case and the behavior on the level surfaces that corresponds to positive value of the parameter is that in this case you do get homoclinic tangencies. And as soon as you do get homoclinic tangencies, you know that it leads to Newhouse phenomena in many cases. And in dissipative case, when you don't have area preservation, the Newhouse phenomena looks like the following. Suppose that you have a diffeomorphism of a surface such that you have a homoclinic tangency, then near this map there exists an open set of diffeomorphisms and the residual subset of that open set where each diffeomorphism has infinitely many attracting periodic orbits. All diffeomorphisms in that open set have homoclinic tangencies, so you have persistent homoclinic tangencies, and there are many other phenomena related to that one. You can say, well, in our case, we don't have a possibility to consider the space of all diffeomorphisms. Robinson, based on the Newhouse ideas, proved that if you have just one parameter family, but that one parameter family is not degenerate, so that hook, when you change the parameter, moves up and down. It doesn't move just sliding along the manifold. In this case, you can formulate exactly the same statement, but in terms of parameters. So there is an open set of parameters in the space of parameters close to the bifurcational value, such that there is a residual set of the parameters, such that the maps with parameters corresponding to that residual set will have infinitely many attracting periodic points, and so on and so forth. Well, it turns out that in our case, we do have Newhouse phenomenon, at least for parameters which are close enough to zero, but negative. So as soon as you started with Kelly-cubic and change it a little bit, so what happens, you lose hyperbolicity in the neighborhoods of singularities. Everywhere else, you will still have a nice invariant field of cones, and that will be inherited from the Kelly-cubic, from the pseudo-Nosov maps. But in the neighborhoods of singularities, everything will be changed, those directions will be lost, and the stable and unstable manifold that corresponds to the points that never enter those small neighborhoods of singularities. Notice that points that never enter small neighborhoods of singularities on Kelly-cubic form some counterset, some hyperbolic set, and that hyperbolic set survives under small perturbation of the parameter. And what happens is that stable and unstable foliations will start to have homoclinic tangencies as soon as you switch on the parameters. So you do have tangencies, but the difference between the classical Newhouse phenomenon and this case is that here we don't have dissipativity, we don't have contraction of volumes or expansion of volumes. So the area is preserved, and conservative Newhouse phenomena, what happens if you have homoclinic tangencies in the area preserving case, turned out to be much harder than dissipative, and it was fully studied by Pedro Duarte, roughly speaking 20 years after the original Newhouse results were obtained. So what Pedro Duarte proved, essentially he proved that you do have the same statements as in the classical Newhouse phenomenon, persistent tangencies, existence of infinitely many special periodic orbits, but certainly you cannot get periodic attractors in area preserving case. And instead of periodic attractors, you should talk about elliptic islands. You should talk about periodic points such that the differential is just a, roughly speaking, a rotation. You can apply KM theory to those. So here is a statement. If you consider the diffeomorphism, well, in this case, he formulated as C infinity statement, but actually it's enough to say C6, for example, just to make sure that you can apply KM theory to all the statements. So you have one parameter family of maps. The picture is exactly the same. And in that one parameter family, there is an open interval arbitrarily close to the point that corresponds to the homoclinic tangency, such that each diffeomorphism with that parameter will have a horseshoe that contains the continuation of the initial hyperbolic saddle, such that you have persistent tangencies associated to that horseshoe, and in particular, the tangency, homoclinic tangencies that corresponds to the initial continuation of the initial saddle are dense in the space of those parameters. And for some residual subset in that interval of parameters, the corresponding maps have lots of elliptic islands, and those elliptic islands will be accumulated on the horseshoe that was constructed. So that's, roughly speaking, the conservative analog of the original Newhouse result. And the question here is that appears immediately is the following. You have that basic set, but that basic set is definitely not canonical. You can find many basic sets that satisfy the statement. So what can you say about the largest possible basic set here? Well, certainly there is no largest possible basic set, because whenever you have a basic set, hyperbolic set, you can expand it a little bit. And it turns out that the notion of a homoclinic class is handy here. So let's take all the basic sets that satisfies this property. Let's take the union of all of those basic sets, and let's take the closure of that union. That will be smallest closed set that contains all the horseshoes that contain a given saddle. Well, I guess here I formulated a different definition, but those two definitions are equivalent. This definition is that the homoclinic class is the closure of the union of all transversal homoclinic points of a given saddle. But once again, those two definitions are equivalent. So it turns out that you can improve slightly the Duarte's result, saying that not only all those properties hold that Duarte claimed, but also that you can choose those horseshoes to be of large Hausdorff dimension. Large here means as close to the ambient dimension of the ambient manifold, as close to 2 as you want. Moreover, standard genericity arguments imply that if you take homoclinic class, then in that homoclinic class you will get horseshoe of very large Hausdorff dimension for many parameters, for open and dense set of parameters. And then if you take the intersection of all those open and dense sets for subsequence of deltas that converge to 2, you get a residual set of parameters for which homoclinic class must be exactly of the Hausdorff dimension 2. And finally, arguments similar to those in Duarte's result shows that not only you can find elliptic islands that accumulate to the saddles, but they also will accumulate to that homoclinic class. So that will be a transitive set of large Hausdorff dimension accumulated by elliptic points, and in a sense that's canonical. That's one is defined by the dynamics uniquely. There is no ambiguity or arbitrary choices here. Why it's interesting? Well, one of the reasons is the following result by Hertz, Taxi and Uris. They considered a little bit different object. They considered ergodic homoclinic classes. Those are not necessarily closed sets. So what you do, you consider stable and unstable manifolds of a given saddle, and you consider all the points where stable and unstable manifolds are defined due to the Pearson theory, for example, and you consider all of those that have such that stable manifold of a point intersect unstable manifold of your saddle, and unstable manifold of your point intersects the stable manifold of your saddle. The set of all those points is called ergodic homoclinic class, and what they proved that if the Lebesgue measure of the ergodic homoclinic class is positive, then this ergodic homoclinic class is necessarily an ergodic component, and moreover, Lyapunov exponents are necessarily non-zero. So it's later we will see that this is a really important thing. Unfortunately, as Ali just explained me before the lecture, this doesn't necessarily immediately imply that homoclinic classes, we define that that we can reformulate that statement for that homoclinic class. So I will state the statement as a conjecture, rather as a theorem, but it's likely that it's true. I believe so. Exactly the same. You have KM theory, and as soon as you have elliptic island, that elliptic island is persistent. In an open set, yes. So you certainly cannot preserve, you cannot preserve integrability, but I'm not claiming that you have any integrable parts. You don't. You just preserve elliptic islands. So of course you have to check some non-degeneracy conditions for those elliptic islands that you create, but that can be done. All right, so all the situation here is very much similar to another family which was heavily studied, so-called standard family. Here is the one. And since, roughly speaking, all the results that we can prove here, we can prove for the trace maps on those spheres, and all the conjectures that can be stated here can be stated there. Let me just to provide the history of the question for the standard family, and we will automatically formulate the same conjectures for the trace map. What is nice about the trace map is that it's polynomial. And I hope that maybe there is a chance to use that fact somehow to produce some results that are harder to produce for a non-polynomial transformation. But it's just a dream, so certainly. And another motivation rather than any claim. All right, so this is the Taylor-Chirikov standard family. When I gave those, when I explained some of the results in the audience where some Russian mathematicians were present after the talk, they told me that I'm not fair and I should call it either Chirikov family or Chirikov-Taylor family. Anyway, those two names are closely related to the family. So you can consider this family in the following way. First of all, for zero value of the parameter, you have an integrable system. So you just have a torus. The torus is foliated by circles, and on each circle you have a rotation, and that rotation is a rotation by the angle that corresponds to the second coordinate. So when you go up to the top, the rotation is by 2 pi, which totally coincides with the identity map that you have on the bottom, and so it's nice integrable twist map of the torus. And then you take the perturbation. The perturbation is the following. You don't change the first coordinate, but the second coordinate will be shifted up and down in the way here. And then you just take the composition of that perturbation and that twist. So shear and twist, shift and twist. And so this is called standard family. And this is probably one of the most heavily studied conservative systems. In one of his talk, Katok said that the talk was called Most Important Problems in Dynamical Systems. The questions about this family was number one. So and also it has really bad reputation. It's known that many people kind of worked for years and then had to switch. All right, so what happens here? When you have that integrable system and then switch on the parameter, due to the KM theory, most of the circles survive, but between of them, other invariant circles with rational numbers and Liouvillean numbers of rotations disappear, and you will get some chaotic regions, some regions where you don't have that foliation. When you increase the parameter, at some moment, all the horizontal invariant curves, even twisted, will be disappearing. And nevertheless, you will still have some closed curves that corresponds to elliptic islands that appear in this picture. And then when you increase the parameter further, you will see on the computer experiments, you will see less and less elliptic islands and more regions that looks completely chaotic, just as for an Usp map or something like that. So the conjecture is actually for most large values of the parameters, you don't have elliptic islands at all. And moreover, you have the system which is ergodic. Well, what most means, well, let's say for the set of parameters that have density 1 at infinity. Reasonable conjecture, no one could prove or disprove that, and moreover, the current state of art is the following. People cannot present any single value of the parameter such that the family would be ergodic for that value of the parameter. And not only they cannot present it, they cannot prove that it exists. All right. So why don't we formulate it for the trace map? Conjecture. For most values of the parameters, small but negative, our trace map restricted to the invariant sphere is going to be ergodic with respect to the natural smooth invariant measure that it has. Well, certainly the current state of art is exactly the same. Another conjecture. Let's consider the set of parameters for which at least one elliptic island exists. We know that this set of parameters is open, right? And we will see later, it follows from another result by Pedro Duarte, is that this set of parameters is actually open and dense in the neighborhood of infinity. But nevertheless, it doesn't claim that the following conjecture doesn't hold. Let's take the set of parameters when you don't have elliptic islands. Its complement is open and dense, but nevertheless the set can be of positive measure, and the conjecture is that not only it's of positive measure, but it has density 1 when parameter tends to infinity. Once again, this is an open question, whether you can find at least one value of the parameter such that there are no elliptic islands. And exactly the same conjecture certainly can be formulated for the trace map. Another conjecture now by Sinai claims that for large enough values of the parameters, or maybe for all values of the parameters, the measure theoretical entropy with respect to the Lebesgue measure, notice that the standard family preserves the Lebesgue measure, since it's a composition of two area preserving transformations. The conjecture is that measure theoretical entropy with respect to that Lebesgue measure is positive for many values of the parameters in a sense. Once again, well, why is it interesting? It's interesting because due to the Peasson theory, as soon as you have positivity of the entropy, this implies that you must have an ergodic component with non-zero Lyapunov exponent. So it implies that you must have some part of that stochastic picture of positive measure, and that justifies the picture that we see on the computer. Because theoretically, nothing contradicts to the completely different picture, that almost everything is covered by elliptic islands, but those elliptic islands have very strange form, and if you go to the smaller scale, you will just have tinier and longer and stranger elliptic islands, and so on and so forth. Total unbelievable picture, but there is no formal contradiction to anything that we know. So if that Sinai conjecture would hold, then that would justify the existence of stochastic C. All right. Once again, open question. Can you present any single value of the parameter such that measure theoretical entropy would be positive? It's known that topological entropy is certainly positive. There are lots of horseshoes. The asymptotics of the topological entropy is calculated. But Lebesgue measure is a very special one. You cannot use variational principle. It just doesn't help much. This is another open question. And certainly we can formulate exactly the same question for the trace maps, and the answer is the same. We don't know. All right. So topological entropy is known in a sense that asymptotics as coupling constant goes to infinity are calculated. There is a paper by Oler Neal where it's calculated explicitly, and it's known that topological entropy is growing, and it's growing with respect to the parameter as log of the parameter or something like that. For the standard map, yes. For the trace map, it's also possible to prove, that's a good question, we didn't do that, but it's possible to prove that topological entropy should approach the topological entropy of the map on the Kelly cubic, which is exactly log of golden mean. In other direction, it goes to 0. Because in other direction, everything kind of converges to the integrable transformation. So it changes from 0 to some constant. But what I said is not written anywhere. It's just that's a good question. How to prove that formally and accurately? That could be a little bit delicate. All right. So another related conjecture is a conjecture about a mixed behavior. So what is a mixed behavior? Suppose that you have a conservative system, area preserving nice transformation of a surface. And we know that if you have elliptic islands, then there is a part of the phase space of positive measure where the behavior is regular, 0 Lyapunov exponents, and the motion is just rotation of a circle, so you essentially know everything. On the other hand, if you have, for example, an Usp map, which is also area-preserving transformation of a surface, then you have chaotic behavior, you have all non-zero Lyapunov exponents, and a completely different description of the dynamics. So, question: can you present a map where both types of the behavior are present at the same time on parts of phase space of positive measure? So both of them have positive measure. Now, C-infinity examples do exist, and they were constructed by Felix Przyczicki, by Liverani. There are some other maps that people studied in this context, not C-infinity, but very much of similar flavor. But C-infinity here is completely crucial, because essentially what people use, they use that C-infinity surgery. So on one part you create one behavior, on another part you create another behavior, and then you glue them somehow using the fact that you don't have any rigidity. Now, if you consider analytic maps, and standard family is certainly the family of analytic maps, as well as the trace map, then the answer is totally hidden from us. There are no examples, any analytic diffeomorphisms of surfaces such that we would be able to formally prove existence of the mixed behavior. And this is the problem that comes from one paper with a list of open problems to another. Okay. Once again, for the trace map, we can formulate the same question, and the answer is exactly the same. We don't know. All right, so what is known? I said a lot about what we don't know, so what we do know. Pedro Duarte proved the following. For the standard family, there is a family of local maximal transitive horseshoes, basic sets, such that is dynamically increasing. So what does it mean? If you have a horseshoe and change the parameter a little bit, that horseshoe there is a continuation, natural continuation of that horseshoe. So if you increase the parameter in the standard family and consider that natural continuation of the horseshoe that you had, that the horseshoe from that family will be a little bit bigger. Then you continue for a parameter a little bit further, you consider the continuation, but actually there is a horseshoe which is a little bit bigger that contains that continuation and so on. So that family is dynamically increasing. So let me maybe explain how that family was constructed. For the standard family, you have that twist and you have that that perturbation, and away from the singularities of that sine function, you just shift it in such a way that it's really not hard to construct the cone field, the invariant cones where you expand. But as soon as you come to the small neighborhood of the singularities, the dynamics is totally non-hyperbolic anymore. You just don't have those invariants of cone fields. So the trick is just to say, okay, let's consider the points that never come to those small strips. And certainly you have invariant cones, you have horseshoes, and that's exactly the family of those horseshoes. For the larger, when the parameter increases, that strips that you can consider can be taken smaller and smaller. The neighborhoods where cones can be constructed become larger and larger, just because if you multiply sine by a huge function, you will have only small interval where the derivative is smaller than delta, and everywhere else the derivative will be bounded from below. And that's exactly the family of horseshoes that is constructed here. From that picture, you can see now that it's probably not surprising that when the parameter goes to infinity, the Hausdorff dimension of the constructed horseshoe goes to 1. And that's exactly what is written here, and moreover, written in a quantitative way in terms of that parameter. And besides, those horseshoes fill the torus in a sense that they form delta net of the torus, where delta becomes smaller and smaller when the parameter becomes larger and larger. And that's also not surprising when you keep in mind that picture, that construction. So you have all those properties. So you have that skeleton of the stochastic C. Moreover, you can prove that actually for the residual set of the parameters in the neighborhood of infinity, the horseshoe is accumulated by elliptic islands. And that follows from the statement that actually for those horseshoes, you do have persistent tangencies. Now, if you have those persistent tangencies, then, as we will discuss later, perturbation of the tangency creates elliptic island exactly in the same way as in a dissipative case, the perturbation of a tangency creates a sink. And then you can construct those elliptic islands accumulating to the horseshoes. Well, let's now improve that a little bit. Once again, that horseshoe is in no way canonical. You can add a little parts to that horseshoe. So let's add as much as we can. And then we will get the following result. Let me show it all. So for many parameters, for the residual set of parameters in the neighborhood of infinity for the standard family, what you can do, you can take that initial horseshoe that was constructed by Duarte, and then you can increase it a little bit. You will find a different horseshoe, which is a little bit larger. Then you can increase it a little bit, and you find a larger horseshoe, and so on and so forth, such that, well, for the very first one, we have all the properties that were listed in the Duarte theorem, but that sequence of horseshoe will be increasing, not only in terms of inclusion, but also in terms of Hausdorff dimension. The Hausdorff dimension will tend to 2 when you take that nested sequence of horseshoes. Notice that here parameter is fixed. We don't send the parameter to infinity. So for fixed parameter value, as you tend larger and larger, come to larger and larger step of the construction, you get Hausdorff dimension larger and larger. And hence, if you take the union of all of them, and this is, if you take the closure of that union, that will be exactly the homoclinic class of one of the saddles in the very first horseshoe, for example, then that union must have Hausdorff dimension which is exactly equal to 2. And moreover, it's a nice set in the sense that not only Hausdorff dimension is equal to 2 because of some part of the set, but any point of that set has local Hausdorff dimension which is equal to 2. That directly follows from the construction, since for horseshoes we have that property. And finally, we can manage elliptic islands to accumulate on that homoclinic class. So what we proved, roughly speaking, is that stochastic C of the standard family has maximal possible Hausdorff dimension. The big question, as I mentioned before, is whether stochastic C has positive measure. And now you can see the relation of what we did here with that result by Tazibi and co-authors. If you manage to prove that particular homoclinic class has positive measure, then that would most likely imply that you have the solution, you have example of the mixed behavior for the analytic family. All right. I do. Well, I have some ideas, but those are, I don't. No. Okay, exactly the same result holds for trace map. So for the trace map, instead of sending parameter to infinity, you send the parameter to 0 from below, and your phase space starts closer and closer to the internal part of the Cayley cubic, and the map starts closer and closer to the Tsevdanov transformation. And I will not read it. It's exactly the same list of properties. You have those hyperbolic horseshoes with larger and larger Hausdorff dimension, elliptic islands, so all the same. Okay, how can you obtain the result like that? Here is the formal statement that you need to use. I don't want you to read what you cannot probably read. I want you to read only the last part, which I hope you can read. And the last part means the following. There is some renormalization procedure related to homoclinic tangency in the conservative case that allows you, instead of arbitrary map, to consider area preserving a no family. So roughly speaking, if you take a huge microscope and willing to wait for a long time, then you take small neighborhood in nearby the homoclinic tangency. Make a small perturbation with respect to your parameter. Wait for a long time until the first return map will be appearing. And you will see something which is very close in CR topology to the conservative Henon map. So if you have any property of the conservative Henon map that preserved under the perturbations, then you can claim that that property holds for the map where conservative homoclinic bifurcation happens. And notice, for example, that the Hausdorff dimension of a horseshoe is something that depends continuously on a map, even in C1 topology. And therefore, if you can prove existence of horseshoes of large Hausdorff dimension for this particular family, then it immediately implies existence of the horseshoes of large Hausdorff dimension for this. Say it again. No, it's no. Sorry. A is a parameter, so A is fixed here. So you have one parameter family of two-dimensional maps. All right. So claim is exactly like that, and this was the first three statements were exactly the important part of the Duarte paper where he studied the conservative Newhouse phenomenon. The statement is exactly like that. If you have that area preserving a no map, then there is a range of parameters where you do have persistent homoclinic tangencies, and besides you have horseshoes of large Hausdorff dimensions. That's kind of an addendum to that statement. So how can you work with that? What helps a lot is that actually there is only one non-trivial quadratic family. Any other can be obtained from that family under some change of coordinates and change of in the space of parameters. So for example, you can consider this family instead of the NO family. And for this family, what is nice is that after some renormalization, after you take a very specific microscope, this is a microscope that I am taking, after you implement that affine change of coordinates, this is the family that you will get. Why this family is nice is because if you treat delta as a small parameter, then this is a higher order terms, and here you have, roughly speaking, the shift of the identity under the action of this vector field for a very small time. So the behavior of the family must be directly related somehow to the solutions of this differential equation, and this vector field is easy integrable vector field. You can explicitly see how it looks like. So okay. So for this vector field looks like the following. You have one saddle, you have a saddle connection, and inside you have a point which is elliptic point, and so you have that family of closed curves here, and you have some other family around. So this is an integrable vector field, and so what you do, you take a perturbation of this vector field, roughly speaking, with a time periodic vector field. So you take the time one shift and make a perturbation of the time one shift. So what is known, so after you make the perturbation of the time one shift, what happens, you have a splitting of separatrices. Now separatrices are stable and unstable manifolds of that fixed point. And you have that splitting of separatrices that was studied heavily in terms of standard family by Lazutkin and Gelfreich. And their method were improved by Gelfreich and applied to this particular family. And he proved that the splitting is really nice. Namely, there is a neighborhood and normalizing coordinates such that the map in those normalizing coordinates is just a shift, and the curves that you see there are just stable and unstable manifolds of that saddle. So moreover, it's not just looks like a sign. It is a sign up to higher order terms. So the splitting is exponentially small, but you can nevertheless describe it very nicely. On the other hand, in the neighborhood of the saddle, you have Birkhoff normal form that allows you to reduce everything to almost a linear hyperbolic transformation up to some coefficient which depends only on the first integral. So you have two nice normalizing coordinates, and so you can change coordinates from time to time to study completely the dynamics here. And that's what if you do that, it turns out that you can construct the following family of horseshoes. So let's take a small rectangle as on this picture. So this is just a microscope. And then let's consider the first return map on that rectangle. Well, first of all, the image of that guy is going to be here just after the very first transformation. So on the other hand, if you consider those points that for the first return must actually travel all the time, then you will get that rectangle first in this coordinate system that will be that smaller rectangle. Then you just shift it, and then you come back, and that will be a really tiny small leg here. So you have a horseshoe, which is really strange. You have one leg which is huge and one leg which is very small. Due to the fact that you know everything about those normalizing coordinates, roughly speaking, you have very nice asymptotics, explicit asymptotics of the size of this guy in these coordinates where the size of the rectangle is of order 1. The size of this guy is of order 1. And you have asymptotics of this guy and asymptotics of the gap in some natural terms. So by those terms, we can take, for example, the eigenvalue of this saddle. So, but whatever it means geometrically, it's just think about some parameter, some explicit parameter here that tends to 1, for example. So we have a parameter that tends to 1 that parameterizes the family of these pictures. All right. Now the problem with this horseshoe, so here I just want to take this horseshoe and send it to itself. So I consider the first return map. The first return map is just a horseshoe of this form. And we want to take this horseshoe and as our hyperbolic set. Now the problem with this horseshoe is that one of the legs is really big and one of the legs is really small. And moreover, it's much smaller, this leg is smaller than this gap, which means that the thickness is going to be very small, because how do you calculate the thickness? You take this part and divide it by this part. And it's going to be really, really small. So you cannot directly imply the Newhouse gap lemma in order to establish, for example, persistent homoclinic tangencies. Well, Duarte solved this problem brilliantly using the definitions that Guga Moreira gave in order to give an example of dynamically defined countersets where the thickness is smaller than 1 and product of thicknesses is smaller than 1, but nevertheless they have persistent tangencies, persistent intersections. So he suggested to consider separately left thickness and right thickness. So you consider separately the ratio of these two guys and of these two guys. So in this case, in our case, one will be really small and one will be really big. So well, now we have a competition. And in that competition, assumes that you have two countersets such that the product of left thickness of one of them with the right thickness of another one is bigger than 1. And vice versa. Right thickness here and left thickness here give you the product which is larger than 1. This is enough to claim that you will have persistent tangencies. And that's exactly how Pedro Duarte proved existence of persistent tangencies for the conservative Newhouse phenomenon. Unfortunately, in his construction, the horseshoe that was constructed was very explicit, and you could actually calculate the Hausdorff dimension, and you'll get some number smaller than 1, smaller than 2. But it turns out that you can improve the construction. You can tweak it here and there in such a way that you increase the Hausdorff dimension. So, well, in order to know how to tweak it, you need to know how to estimate the Hausdorff dimension if you know the left and right thickness. You have seen the Moran's formula in the other course already, and this is, in a sense, analog of that Moran's formula. So if you have two countersets, if you have a counterset with two different thicknesses, right thickness and left thickness, then you can find the solution of this equation. There is exactly one solution of this equation, D, and it turns out that Hausdorff dimension of that counterset is necessarily bounded below by that D, by the solution of this equation. Now, if you put left thickness to be equal to right thickness, then this equation and this statement will give you immediately the inequality that we have seen before that relates the usual thickness with the Hausdorff dimension. Namely, if thickness goes to infinity, then Hausdorff dimension of a counterset goes to 1. So this is a direct generalization of that formula. Unfortunately, it's not very explicit, so for our purposes, we can make it uglier but more explicit. Namely, that implies that Hausdorff dimension is necessarily bounded from below by whatever is written there. And in our case, in terms of that parameters that I mentioned, which is slightly larger than 1, right thickness is of order 1 over lambda minus 1, and left which is very large. And left thickness is of order lambda minus 1 to the power nu, where power nu is some positive number, which is the parameter of the construction. You can choose it as close to 0 as you want. And then you just substitute and get that the thickness is bounded from below but by 1 over 1 plus nu, and nu can be taken as close to 0 as you want. That's it. You get the counterset such that it's a product of a horseshoe such that it's a product of two countersets, and Hausdorff dimension of each of them is close to 1. So the Hausdorff dimension of the horseshoe is close to 2. And that's it. Thank you.